Okay, hi everyone. My name is Charlie, and my topic today is that water mass transformation in the Iceland Sea, contrasting to winters separated by 4 decades. So before going to the topic today, we need to know where does water mass change. So this is the figure of the thermal helium circulation. And the red line is the warm surface water flow, and the blue line is the cold deep water flow. So we know that when deep water and surface water meets, their mass will change and also their density will change. So we know about the areas like here, here, here. They will change their mass. But what about the line here? We know about the south of the ridge here, but we don't know anything about the north here. So scientists started their analysis to figure that out, that the potential density of the seawater has dropped in this area that in the last 4 decades. And they discovered that the source of the water jets has changed. Like the resources have changed from Iceland Sea to Greenland Sea. So things we want from the north of the ridge. And the number one is where and how the water mass transforms. And the number two is why the source of the water mass changed during the last 40 years in this area. So why? Why do we choose that 1974 and 1975? So because it is the only winter that it has enough data to coverage the full winter data. And there is also a reason that it somehow didn't show up, that 1974 and 1975 are the coldest year during the last 70 years. So it has the difference, much clearly difference between the present and the before. And how do we collect the 1974 and 1975 data? We use it we collect them in the old-fashioned way, like we use the data from the historical hydrographic data sets that was collected by vessels that it was since 1950. And now we use that in 2015 and 2016, we use the autonomous ocean gliders. So the difference between these two data are the data in 1974 and 1975, that the width is 0.5 latitude and the length is 1 longitude. But in now, like the 2015 and 2016, the width is 0.2 latitude, but the length is 0.5 longitude. So we can know that in 1974 and 1975, we have the low spatial resolution. So in 2015 and 2016, we have the higher resolution of the data, so we can see the data more clearly. And how do we fix the inaccuracy of the 1974 and 1975 data? We use the ERA5, that's not ERA5, it's ERA5 to reanalysis to solve this problem. The ERA5 is the 5th generation of the meteorological reanalysis project that was organized by European Center for Medium Range Weather. It can dictate the sea ice concentration and the surface turbulent fluxes. So we use them to fix the errors from 1974 and 1975. And there are many major jets in Nordic seas. The only jet we need to know is the NIJ, the North Icelandic jet. And it was colored in light blue, so which means it's cold currents. So why do we assume that the jet's result change? We can see from here, the yellow line is the flow of the data, and this is 2015, and this is the 1974. You can see that the density has dropped very lot from that 40 years. So the average of the potential density of Nij is around 27.9 to 27.95 kilogram per square meter. And it won't change over time. So it would always stay the same nuts in the future. And the overflow water limits of the potential density is 27.8 kilogram per square meter. Which means if the water mass is bigger than this, that it could be a source of the jet. And we can see from here, this is the line of the 27.9 line. So we can see that the 27.8 here, this is the line. So over this range, the water would flow with the jets. And we can see from these two paragraphs, the water that is bigger than 27.8 are gone. That during the April 2016, that because the water that bigger than 27.8 would flow when it is bigger than this range. So you can see from here, the water mass that is between that 27.9 to 20, that is bigger than 27.9 is still here. So we can see that it didn't go with the flow now. So we can assume that the flow that's overflow with the jet are in 27.8 to 27.9. So which is not the potential density of the Nij. So we assume that the source has changed from Iceland Sea to Greenland Sea, which is the colder mass. So it has more denser seawater. So why did the potential density of the water mass in Icelandic Sea change? It was because of the reduced sea ice. And this is the photo of the sea ice extent in 1970 to 79. We can see that it was all over the sea range to the Greenland Sea and Iceland Sea. So we can know that because in the Arctic region, that when the land blow wind, it has much colder wind than the seawater in the Arctic ridge. So when the land blow wind, it will change its heat with the sea. So the seas can express its heat with the cold air. But now that 2010 to 19, the sea ice reduced, so we can't have enough distance to change the heat with the water here. So the water would become warmer here. So the water here would become warmer and warmer because they absorb the heat. They can express the heat. And the red line is the sum of the first two components of the Fourier transform representing variability. So this is the heat flux in the last 70 centuries. And you can see in the winter from 1974 and 1975, the heat flux changed a lot here, but in 2015 and 16, it changed less. So we can see the periods are greater than the 35 years. So the outcome, that is because of the reduced sea ice that caused the density of the seawater in winter drop, and it caused the resource of the water jets change. So we can see the which we have gained. Yeah. So this is the reference, and thank you for listening.
Can you speculate the density in this area for next few years and share your thoughts with us?
Okay, I guess the density.
Yes, and in this area for next few years.
Oh, so the paper didn't mention the future prediction in their analysis. So they just use the data before. My guess that the density might become more and more lower.
You think what impact will due to thermal highland circulation because the ice reduced?
What would cause the thermal helium circulation due to the ice reduced?
Reduced, yes.
Okay. Oh, you mean what would that sea ice reduced cause to the thermal helium circulation? Because this is a big range figure, and in here, this is just a small figure. So this is the current of the Nordic Sea here. So so it doesn't mean that the thermal helium circulation it is not the same meaning of the data.
Okay, you say Fourier series, and I want to know what's the meaning of Fourier series about this problem.
Okay, so what's the Fourier transforms means in this? So Fourier transform with that it is a math question. It will integrates the data into a period, like combine it into a period, like using the integral thing.
Oh, okay.
What is the Nij, the jet, infer?
What's this mean?
What is jet?
Jet. Okay, jet is a more smaller currents but more faster currents that appear in the shallow narrow narrow ridge.
Reach. Okay.
I think this paper was sort of intermediate difficulty, and I think Charlie has handled this physical oceanography topic very nicely. Because yesterday when I was reading the article, I was really like, what is it about? But I think in this presentation, he was able to explain us. The most important thing is he was able to explain us carefully how this data led to his conclusion. That was very important because these data, they are not very simple, like a number of specimens, something like that. You see these are potential density things. So this is a little bit abstract, but still he was able to explain it clearly. So I think he did a very nice job. And I also think his introduction is very interesting. So you see that he added a lot of these images to brought us into the world of Atlantic Ocean. So I forgot the name. So the polar area. So that was very nicely done, very nice. But I think in the introduction, maybe you can tell us one more thing, because in this region, you see that there are so many, there are many different currents. So why should we care specifically about an IJ? So what's the importance of this jet current? Why should we care about it? And then, okay, and I forget where you mentioned that, because in one slide you started to talk about overflow water, right? At that point, I was a little bit missed, because you have not mentioned anything regarding overflow. So because I think you still have time, so next time maybe you can explain us what this overflow is about. Yeah, maybe that's related to the importance of an IJ. And then regarding these, so these are all very nicely done. So you see he always has this very simple, short, concluding remark that lead us from, especially his concluding slide. So many animation. Okay, this one is really nice. So it tells us what is the flow of logic. However, in this slide, regarding this turbulent heat flux, I know you have used this animation to bring us into the concept. However, probably you need to tell us when the heat flux is higher, what does that mean? Does it mean more flux to the air or to the ocean? Which direction is it? Yeah, and the other way around. And I think you want to use this to tell us that today we have a warmer ocean, right? Okay, and then one more thing is, next time for potential density, I will appreciate you use the term lowered instead of dropped. Because sometimes when I see the term dropped, I have the immediate connection that the potential density will have a higher value instead of a lower value, you know? Because when we say a density is higher, it will drop. So it will give me this connection. So try to avoid the term drop. Use lowered, okay? But otherwise, this is a very nice talk. You see very rich image, short sentence, clear logic. So I really appreciate your talk. Thank you, Charlie.